Thank you very much for the kind introduction, Mr. Chairman. Ladies and gentlemen, it's a pleasure for me to give this talk here today. Also, I don't have a medical background, I have an engineering background, but I will try to focus the topics of the presentation on medical applications so that we can see some parallels. My talk is structured like this. I will start first with a short introduction. Then I will show you our collaborative research center, and then I will show you some results, and I will close with a brief summary. Like you know, the additive manufacturing, or so-called 3D printing, right now has a very high medial interest. As you can see here in some newspaper article, for example, The Economist, you see they say the third industrial revolution, or there are other fancy topics like in the future everything could be produced in the kitchen at home. So the interest in 3D printing is quite high, but you also can do this in numbers. For example, the number of granted patents or patent applications increased, or increasing, it's the wrong word, it exploded the last years. And you have now a large number of patents in this field, as well as Google Trends. You can see the difference between the words. On the one hand, everybody is searching for 3D printing or 3D printer, but additive manufacturing, which nearly the same, but a little bit more scientific way. You don't have this hard increase of Google searches. So what we can see in this diagrams is that there's a large interest in this topic. But where are these techniques even applicated? You can see here some examples. We have a very well establishment in things like automotive sector, as you can see here in this picture, with about 19% of industrial ratio. Then you see some things like consumer products, this mobile phone cases. You can individualize them and print them out. But we also have medical devices with about 16%. And in medical applications right now, we have two major fields. On the one hand, we have the dental applications, and on the other hand, we have hearing aid devices, which are 3D manufactured. And so we have some parallels to the medical sector. Here you can see the process chain we would like to realize in future. You can see a CT scan of this skull with a defect in the jawbone, and you see that you now have the possibility, based on the CT scan, to model an individualized implant. That's not really difficult with the computer software. You can do this very quickly. And then furthermore, you have the possibility to individualize this implant by structures, maybe for getting a defined surface roughness, to adhere tissue in this area. But this is only done in the computer. Right now, you have this additive manufacturing processes, and there's the bottleneck right now, because additive manufacturing processes have a high potential, but to meet requirements you need for printing implants, it's quite hard. And I will show you in this talk why. Requirements you need for printing such a complex implant are, for example, you need defined part properties. So if you give a geometry into the printer, you need predictable and reliable part properties you get out of the printer. There's no way that you have some variations in part properties or something like this. You need them defined. Then you need a close process monitoring, beginning with the material you want to process up to the usable part. You need a closed control of all steps done. And then you need approved materials. Not every material can be used for working as an implant. That's the challenges we have to meet, and right now we have still a lot of different additive manufacturing processes, but they have all the same problem. We don't have enough basic knowledge about them to meet these hard requirements. So our collaborative research center was established by the German Research Foundation. We have the scientific aim to do basic science in the field of additive manufacturing. Right now we are in the second granting period, which runs out 2019. These are 15 sub-projects with a very comfortable funding of money so that we can do real good research activities in this field. Today I want to focus the selective beam melting process. We have a large variety in additive manufacturing processes. Professor Mitchell showed this yesterday. And in our research center, we focus the beam-based processes. The beam-based processes all have the same principle. You have first the material coating. It's a thin layer of powder. It can be a metal powder or a thermoplastic polymer. Then you have a local energy input realized by a laser beam or by an electron beam, where the material is molten in some areas, and then your building platform is lowered, a new layer is coated, and the process begins, repeats. And here we can see this for this produced part. So you can build up layer-wise parts with very high complexity. The most advantage of the powder and beam-based processes is that you don't have any limitations in geometry. You don't need support structures, especially for polymer parts, and you have a very high resolution, which is limited by the size of the powder you have or by the thickness of the layer you want to manufacture. Furthermore, for medical applications, you have a large building volume with approx this numbers, so you can realize even larger parts. But there are also some restrictions we have to overcome, and most of the restrictions are from material side. You can see for polymers, we only can process right now some semi-crystalline materials, mainly PA12, which has about 98%, covers the market with about 98%. And then we have some polypropylene or polyether ketone applications, but the variety of material is very limited. For metal applications, we have some more materials, even some which are allowed to be implanted. Most of them are titanium materials, but even the metals right now don't have enough variety in materials. And furthermore, we have the problem that we have very limited simulation tools. So we can design our implant, but we cannot simulate the building process. So that's a real limitation, because we have to do a lot of try and error work and something which is very cost intensive. And the technology, the production technology right now is not reliable, even if you can't simulate it. Here I want to show in brief the difference between the processing of a polymer or the metal. The principle is always the same. You have a beam source and you have a powder material, but polymers have a very unique melting behavior. They can be solid and molten in one state. You have a two-phase mixing area at the same temperature. It's marked with the building chamber. In this area, the polymer isn't solidified, but it don't have to be molten. So you can have this two phases area, like you see here. This is not molten. This is in molten state. And for metals, you don't have this peaks. They are close together, so the metals are exposed with a laser beam or an electron beam. Then they are molten, and right now the beam is away. The material solidifies again. For polymers, that's not the case, so they are quite more difficult to process, and they have a large time-dependent material behavior. So there are a lot of questions, but what we are doing is we have to focus on a few of them we can treat with our science work. And our focus is, on the one hand, we only investigate powder materials. Then we only investigate beam-based processes, and we do this for plastics as well as metals. And our main challenges are to increase the process repeatability, the mechanical properties. We want to get better internal stresses or surfaces of the materials and the resulting parts, and we want to have a closed processing control even with a simulation tool. How we want to do this, we have 15 sub-projects which focus on 3 different areas. The first area are the powder materials. In this area we produce our own powders and try to increase the variety of materials which are usable for the process. Then we have the processing area, where we on the one hand investigate the laser-based processes for polymers and metals as well, and the electron-based processes. And then we have another field in the processing area which is called combined process. This is a little bit more in future. There traditional manufacturing processes like bending or die casting are linked with additive manufacturing, but I won't discuss this in detail today. And our third group is the simulation group, where we on the one hand simulate the processes and on the other hand the part behavior. So now I want to show you some results out of these three topics. And I will start with the powder materials, and I will focus polymer materials, because polymers are quite difficult to get them in a powder stage, because they have problems with the surface tension, and they are sometimes they are not brittle enough. For metals, these problems aren't as significant. Metals have a very good surface tension. They have this balling effect, and if you have a melt and give a gas into it, and then you have a spray, and the metals ball really good, and you get round spherical powders. But for polymers, you can't do this, so you need other ways to do it, and we do this by grinding the polymer. You first have a very big granular polymer, then you grind it in a mill, and then you get a lot of irregular shaped small particles. As you can see here, and these irregular shaped particles are not usable for the process, because as you can imagine, if you have this irregular shaped particles, the packing density of the powder is quite low, and you have the problem that your surface roughness of the parts is very high. So there are a lot of edges in it, and that's not very good for most of technical applications. So we have a rounding step which was established in our research center to get the particles spherical. And even with this rounding step, we have the possibility to do some particle functionalization, for example, to add a flow agent or to add some other ingredients for functionalizing the material. And as you can see here, in the microscopy pictures on the left side, the very irregular shaped powder can be transferred into this spherical powder with very good packing density and size distributions like the diagrams show. But what does this mean for our produced parts? You can see this here. These are single layers molten by our produced powder, and you have this ground irregular shaped powder, and you see you don't get a closed molten state. You have a very high porosity in this layer, and it's not usable for technical applications, especially for implants. But with the rounded powder, you get a much better packing density, even a denser molten layer. And if you functionalize this powder, the rounded powder, you even can get a very dense, the highest density within this experiment. Another way is to functionalize powder as well as a previous compaction of the powder. With this technique, you can get very dense layers with nearly no porosity. So this was an example how the process interacts with the material. And now I want to show you some things about the processes itself. And if you remember, we have 3 major steps in our beam melting processes. The first is the powder coating. And you can see this for polymers. State of the art is to coat every polymer in the same way. Even if it's a polyamide or it's polypropylene, you coat them everything in the same way. And we tried to investigate what happens if we meet the requirements of our polymers. So we know, okay, this polymer has a little bit larger particles than the other. How can we meet these requirements? For example, by adapting coating parameters. And as you can see here, by adapting coating parameters in the right way, you can get from a part with a very high porosity, where you can see even the single layers, to a part with a well-distributed porosity. The layers are better connected, and so you have a better property distribution over the whole specimen. The specimen was a cube, and these are some CT scans of this cube. If we go a step further, the exposure step with the laser beam, for metals, the exposure can be done very fast. Metals you can give to them a very high gradient of temperatures, and this doesn't really matter for the structure. They are not as limited as polymers. But for polymers, we have the problem, if we have a very fast processing, then we have some, we have problems to conduct the heat into the surrounding powder, and then you have a very high peak temperature within the material, as you can see here, with approx over 400 degrees Celsius. And for a polymer over 400 degrees Celsius, this is next to the degradation level of the polymer. And degradation always means that the mechanical properties decrease, and even some very bad material properties appear in the later part. So we decided to orientate our process not on an energy level you put in the material, and we try to get a new processing strategy where different processing speeds are compared. And you can see this in the cross sections of single layers. If you have a very smooth and slow energy input, like in the first picture, you have a very thick molten layer. And if you do the energy input very fast on the same energy level, then you only get a thin layer. So here we could show that the time distribution of your energy input is from major interest to guarantee reliable part properties. For metals, I only want to show this in brief. We don't have this problem in that way, because as you can see, we have a lot of different speeds, processing speeds you can use on a lot of different energy levels, and you always get this green dots, and green dots always is an indicator for good parts, as you can see in the middle, and good parts are very smooth in the surface and mechanical reliable. So what does all this results mean for our simulation of the parts and the processes? First, I want to show you how we do our simulation. We are working with multi-scale simulations. So first we have a very simple simulation. It's called the DEM simulation of the powder coating process. And then we have the lattice-Boltzmann simulation of the exposure process. And these simulations are linked together so that we can derive with infinite element simulation the temperature fields which appear during the processing. And now I can show this in detail. This is the simulation, how the powder behaves during the coating process. What you can see in this green appearing is the part. It's already molten, or in this case solidified because it's a metal part. But then you can see how the powder is coated over this molten area. And for us, it's from a major interest, because with this we can predict the packing density of the different powder particles. And it's clearly when you have a high packing density, you even have better part density. So there we can test different size distributions of powders in the interaction with the coating process. Another thing is the exposure. This should also be a video, but it's not running okay. So I will show it here with the picture. Here you can see the laser beam, which penetrates into some powder particles. And with this simulation, we were able to predict where the energy input is large enough for melting the powder, as well as things like effects if the powder can fuse together, or if we have some defects in the molten state. And last but not least, we have this simulation of our temperature fields, which appear during the laser exposure. You can see this here. For a polymer material, the laser writes or exposes the geometry. And the red temperatures are the temperatures which are critical for our polymer. In this kind of temperature, you can get degradation effects. And you also can see how a new layer is applied and how the thermal interaction between new and previous exposed layer appears. So let me summarize the talk. By investigating powder materials, processes, simulation tools, as well as part properties, we now have a really good basic understanding of the powder and beam-based processes. And this is an important step for us to get multi-material parts with defined properties in the future. And maybe this defined properties are usable in the field of medical applications as well as other technical applications. Yeah, thank you very much for your attention.
This talk is now open for questions. Yes?
In the powder production process you showed at the beginning,
Yeah.
You seem to be attempting to have a particular particle distribution from a single powder production process.
Yeah.
Have you found any advantage of formulation as a way of achieving a better, more effective particle distribution than rather than attempting to make it in a single magical step that gives you the ideal particle distribution?
Yeah, we use the grinding process, but it's very ineffective. Most of the distribution you have to throw away, and only a few of them is usable. But we also have another process. It's called the melt emulsification, and with this you get better size distribution with less loss. Yeah.
That's another question.
Yes, we have time.
What would you see as the ideal polymer material? What would be its characteristics?
I'm not sure. The polymers, they have good properties. For example, the tensile properties or special stiffness things. But polymers right now are one step behind the metal materials in additive manufacturing. So polymers are very established in 3D printing for home use or something like this, because they are easy to handle. But with beam melting processes, polymers behind the metals. Or behind the metals.
So how could they be improved? That's really
Okay, how you improve them? You have to find a polymer which is really designed for the selective beam melting process. For example, all the types of polymers you use in injection molding, you have a large variety in different types of polymers, and they are all designed for different processes. And for additive manufacturing, the market right now is not big enough for designing a unique polymer for this application. So maybe in future times, if we have more markets to sell these polymers, the material manufacturer will design polymers which are especially designed for beam melting process.
I mean, the polymers that you listed on your slide are all relatively high temperature materials. Required to be heated to a high temperature.
Yeah.
You've selected those because of the properties they deliver, rather than their ease of processing.
Yeah, in this case, the polyamides, even the polyether ketone we choose because of the later on part properties, technical parts, and engine applications. We need the high temperature.
Thank you.
Are there any more questions? I've got a few questions.
Yes.
And they're specific to metal. Have you worked with tungsten?
Right now, we only have worked with titanium and nickel-based alloys, not with this one.
Would it be possible to
Yes.
apply your methods with tungsten?
We can think about it. I'm not an expert in metals. I'm from Polymer Institute, but in our research center we have a large variety of materials, so why not? It would be possible, yeah.
And next question, in your titanium and nickel, which have very, very high melting temperatures, is the beam truly producing melt, or is it sintering the material?
For electron beam melting, we have a really molten state. For laser, it depends on the processing strategy. You can get a melt, but it's quite harder than with the electron beam. Sometimes it's sintering, but there's
so with the laser, it's sintering. And then with the E-beam, with the electron beam, you can produce a true melt.
You can even get a true melt with the laser, but it's quite hard.
It's hard.
Yeah.
Hard to do it.
Yeah.
Okay. Yeah. And just two more quick questions. One is what would be the lower limit on the size of the objects that you can print? For example, let's say we wanted to make a collimator with extremely narrow septa. Could they be 100 microns? Could you build that up?
Yeah, you have two limitations. The one is the size distribution of the powder,
yes.
So you can't get smaller than one particle is. And the another distribution limitation is that is the diameter of your beam you
yes.
use. And if you have both very small, then 100 microns, it's no problem right now.
Okay, and my final question is can you meet with me during the coffee break?
Yeah, of course. It's a pleasure.
Very, very much. Okay, let's thank the speaker again. And we have a coffee break now, and the session resumes at 4:35.